Okay, so let's look at properties of log functions, right? So we talked about what the definition of a log function is. We looked at a couple examples of how to get logs to exponentials and exponentials to log, but we really haven't talked about the relationship between exponential functions and log functions. So what is the relationship between exponential functions and log functions, right? So let's draw our exponential function here. Okay, and our exponential function goes something like that. This is when, again, a is greater than 0 or greater than 1, and then we have our exponential function go this way when a is between 0 and 1, all right, and it goes something like that. So what is this log function? Well, if you remember in chapter 1 we talked about inverses. And really what the log function is our log function is an inverse of our exponential function, right? And graphically what that means is I take this exponential function and I reflect it over this line y equal to x, right? So this is my line y equal to x. And if I reflect this function over the line, what I get is its inverse. In this case, what I get is the log function. So if I reflect this is what I'm going to get. Okay, and in this case, I'm going to get something like that. All right. And so remember, if you remember in exponential functions, this was our point 0, 1. So when we reflect it now, it's going to be 1, 0. Okay. And then this point here, which is again 0, 1, becomes a point 1, 0. So you see what happens again when the exponential function is increasing, the log function is also increasing, right? So there's a logarithmic growth, and here there's a decay. It's kind of like a logarithmic decay, and here we have an exponential decay. So the log functions are nothing but they are reflections of the exponential functions over the line y equal to x, or they are functional inverses of the exponential functions. So then, just like we talked about in exponential functions, what happens to the domain of the log function? What is the range of the log function, so on and so forth? Well, think about it. If you remember, the function and its inverse, the domain and the range get switched, right? So for the exponential function, our domain was here. Go to negative infinity. I can go all the way from negative infinity to positive infinity, and this function continues, right? So that's going to become the range, right? So if you look at my domain here, my range here for the log function, I go down to negative infinity, and I can go all the way up to positive infinity. All right. As far as my domain is concerned, if you look here, I don't go past the y-axis. In fact, I don't even touch the y-axis, right? So it's going to be all positive numbers. So what I'm going to do here is I'm going to write down the exponential function and the log function domain and range side by side so we can compare, right? So I have a to the x, and then I have log of x to the base a. All right, and like we saw in exponential functions, the properties of both are the same, except this is a decay, this is a growth. Okay, so the domain and range and everything else remains the same. So my domain for my exponential function, if you remember, was negative infinity to infinity. Whereas for my log function now, it's only everything to the right of 0, so that's 0 to infinity. Okay. Then your range. For the exponential function, my range was 0 to infinity because it only goes from above the x-axis, so it's 0 to infinity. And for my log function, as you can see, it goes all the way down to negative infinity and all the way up to positive infinity. So it's all real numbers, or negative infinity to infinity. Okay. And then finally, let's talk about the zeros. Do we have any zeros? So we don't have in the exponential function, we had a y-intercept, whereas in the log function, I have an x-intercept. So I have an x-intercept, right? And so for the exponential function, there was no x-intercept, right? So I'm just going to say no. But for the log function, I have an x-intercept of 1, 0. I have a y-intercept in the exponential functions, and that was my point 0, 1. But for log functions, I don't have any y-intercepts, right? And then finally, think about asymptotes, right? for if I have vertical asymptotes in my for my exponential function, a to the x, and let's say this is, for an exponential function, I have no vertical asymptotes, whereas for my log function, I have the line x equal to 0 or the y-axis. Whereas horizontal asymptotes, I have for my exponential function, I have a horizontal asymptote as y equal to 0 or the x-axis, and no horizontal asymptotes for my log function. So these are in general your properties for exponential functions and log functions. Remember, these functions go hand in hand. That is, for every exponential expression, I have a corresponding logarithmic expression, right? I can say log, so y equals log of x to the base a, if and only if a to the y equals x. These two go hand in hand, right? So these functions are linked, they're inverses of each other, and so here are the properties. Now, I just wanted to introduce two notations to you guys, and one is what we call the common logarithm. Okay, and when the base, common logarithm is a logarithm with base 10, so a logarithm with base 10. Okay, so for example, log of x to the base 10, that is a common logarithm. And when we have a base of 10, we tend to just skip it. We don't write it. So this is written as log of x. So if I don't write a base, that means my base is 10. It's assumed that my base is 10. Okay, and this is the inverse of the function 10 to the x. Okay. Similarly, we have what we call the natural logarithm. So a logarithm with base e. Right, and we remember e was your number 2.718, right? So if I have a base e, then that is my natural logarithm. And just like we do here, we don't write it this way, but we tend to write this as ln of x. So ln of x has base e, right? It is the same as log of x to the base e. And again, remember, if I don't mention a base, it assumes that the base is going to be 10. Now, just as this was the inverse of the function 10 to the x, well, this is the inverse of the function e to the x.